Okay, so let's follow the recipe. First step is set up the axis. Second step is create the DH table. Third is apply the formula to compute the homogeneous matrix. So this is what we're going to do next. The first step is assign Zi along the axis of actuation for each link. I believe that's already been done. So if you look here, we've already assigned, well, not assigned there, we've shown there. So let's just draw it. So here, simply assigning axis to the axis of actuation. So theta 1, this will be Z0. This will be Z1. This will be Z2. Okay, that's the first step. Second step is assign the base frame OO, XO, YO, Z0. The Z0 has already been assigned, as we saw. Assign X0 arbitrarily and Y0 based on X0, Z0. So if you go back, we need to assign X0. Now, you could assign X0 to anything in this plane. You could assign it this way, this way. It doesn't really matter. It has to be 90 degrees. It's really your call. So what I did was, I'll just follow my notes. I just decided to assign it along this way. Okay. Again, I said there's no reason why you can assign it. You could assign it this way. That's fine too. Now Y0 can be assigned, which will be actually Y0 will be pointing that way, right? Because X cross Y is Z. But you know the DH doesn't really depend on Y0. The Y0, Y1, nothing will appear in the DH table ever. So you really don't need to assign any of the Ys. It just adds more clutter to the figure. So I'm just going to skip Y0. Okay, so I done with step number. I did this. Now I go to C. Now C depends on the relation between two consecutive axes of actuation. So I can tell you with confidence that you will not see any problem with which are not coplanar. So it's only these two that you need to take care of. Zi minus 1 and Zi parallel, and Zi minus 1 and Zi intersect. Those are the two conditions. So we have to check them in pairs. So let's go back here. Let's look at Z0 and Z1. So that's the pair we're considering. We need to understand if Z0 and Z1 are intersecting or if they are parallel. In this case, they're clearly not parallel. Z0 and Z1 are not parallel, right? Z0 and Z1 are actually intersecting because when you extend Z0, it intersects Z1. So this falls under this category, which means that Xi is chosen to be normal to the plane formed by Zi minus 1 and Zi. So let's go back. So if Z0 and Z1 are intersecting, then X1 is at right angles to Z0, Z1. So if Z0 is this way, Z1 is this way, easier to put it here. We need to find a vector which is 90 degrees to Z0 and Z1. You can see there are only two ways you can do it. One is you could assign X1 this way, or you could assign X1 this way. Right? Both of those will satisfy the 90 degrees condition. And it's really your choice. You could specify it the way you want. Both those are valid answers. Now, just to make my life easy, it just happens that if you assign it this way along X0, then you will make your life easy later on. So I'm just going to assign it like so. Okay, I'll not use this option, but I'll use this option. So X1 is there. So we're done with X1. Next, we look at the relation between Z1 and Z2. So you can see Z1 is like this. Z2 is like this. The question is it parallel or it's intersecting? In this case, it's clearly parallel. Right? If it is parallel, then the rule book says if they're parallel, then there are infinitely many perpendiculars. Choose any of these perpendiculars for Xi. Okay? So what it means is that there are infinitely many perpendiculars. Right? All these are perpendiculars You can choose any of them. Now, you will make your life easy if you choose a specific one. If you choose this perpendicular, the one which passes through the origin of the Z1 and Z2, then actually your DH table will be simpler. So what we'll do is here, we'll choose it to be like this, X2. Okay, we are one step from finishing. The last step, now we are exhausted with all the axes, all the Z0, Z1, and so on. So what we'll do is we will, so we're done with 3, and we go to step D. We need an end effector frame. Okay, so that would be the, here n will be, I believe 3. So attach Zn to be the same direction as Zn minus 1. Okay, so let's do that. So it's saying attach Z3 in the same direction as Zn minus 1, Z2. So Z3 in the same direction as Z2. Once you assign it, then try to understand the relation between Z2 and Z3. Is it intersecting or it's parallel? In this case, Z2 and Z3 are parallel. If they are parallel, then assign X2 such that it is one of the perpendiculars. So in this case, there are infinitely many perpendiculars. Choose the perpendicular which is passing through the origin of Z2 and Z3. So that would be here. Instead of this, this is X3. Okay, so this way we've pretty much set up Z, all the Z's, all the X's. You could go up and set up Y0, Y1, Y2, Y3, so on by the right-hand rule, but really it's not required because it's just going to add clutter to the figure. AI, alpha I, DI, theta I, 1, 2, 3. Okay, so the other figure which has helped me is this one. Zi minus 1, Zi, Xi. This is for AI, alpha I, and then we have Xi minus 1, Xi, Ci minus 1, that would be for Di, theta I. Okay, so let's get started. So I equals 1. So we need the angle between Z0 and Z1 along X1. So Z0 and Z1 along X1. Okay. So this one might need some work. So Z0 is up, Z1 is to the left, and we need the angle along X1. So we need to, again, if you want to find the angle, this is the angle. It's the angle between Z0 and Z1 in the counterclockwise direction. So that is, as you can see, it is 90 degrees. So that's, sorry, it's alpha I. Then it's the distance between Z0 and Z1 along X1, but Z0 and Z1 intersect. So that's, the distance is 0. Okay, next, the angle between X0 and X1 along Z0. So X0 and X1, X0, X1 along Z1. So the distance between X0 and X1 along Z1 is what? Is that right? No, my bad. I minus 1. So I is 1. So I minus is 0. This should be along Z0. Okay, so the distance between X0 and X1 along Z0 is basically this distance. It's L1. And the angle between X0 and X1 along Z0. Now, the angle right now is 0, but because this is a revolute joint, it will actually rotate, right? So X1 will rotate. So the angle is going to be different. It's actually going to be parameters by theta 1. So theta 1 is, and get the distance. Let's follow to the next link, link 2. So I put I equals to get A2 and alpha 2. So we need the relation between distance and angle between Z1 and Z2 and X2. So Z1 is here, Z2 is here, and X2. So X2 is this way. Okay, so first of all, the angle between Z1 and Z2 along X2. So you can see that if you look at this from here, this way, then you can see that Z1 and Z2 are parallel. And if they're parallel, then the angle is going to be simply 0. The next is the distance between Z1 and Z2 along X2. So this is going to be the distance. The distance is given as L2. This is L2. Okay. Next, let's figure out theta D2 and theta 2. So I put I equals 2 again. So the angle and distance between X1 and X2. Let's look at X1. It's here. X1, X2 along Zi minus 1. So Z1. C1 is this way. Okay, so first let's look at the distance between X1 and X2 along Z1 along this axis, okay? Right, so you can see that X1, X2 actually pass through each other, well, X1 passes through X2 if you extend it, which means that the distance along this axis will just be 0. And next is the angle between X1 and X2 about Z1. Okay, so if you look at it this way, in this fashion, right now at this instant, X1 is parallel to X2, which means that the angle is 0. But it's 0 when theta 3 is 0. When theta 2 is 0, right? When theta 2 is changing, X1 will change. The angle will change to theta 2. So this will be theta 2. Okay, and finally, we need to do link 3. So I equals 3. So let's look at A3, alpha 3. So for that, I need put I equals 3. So Z2, Z3, and X3. Z2, Z3, and X3. Z2 like this, Z3 like this, X3 like this. So first of all, the angle between Z2 and Z3 along X3, that's going to be 0. Sorry, the distance, my bad. Okay, I reversed this, my bad here. This will be L2, 0, because this is the AI. So the distance is this, L3. And the angle is, since Z2 and Z3 are parallel, it's going to be 0. Okay, and the final thing I need to do is figure out the relation for D3 and theta 3. So I put I equals 3, X2, X3, X2, X3, and Zi minus 1, so Z2. X2, X3, Z2. So first of all, the distance between X2 and X3 about Z2, that's simply 0. And then the angle is going to be function of theta 3. So I'll put theta 3 here. So this is my DH table. Okay, the final step is to, so this is step number 2. This one was step number 1. And the last step, number 3, is to use the DH transformation formula, this one. Okay, so it's a 4x4 matrix. You need to put I equals 1, I equals 1, I equals 2, and I equals 3. So we have I minus 1. This is like a big 4x4 matrix, which I will not write down. But in this matrix, you need to put I equals 0. You will get I 1 with respect to 0. It will be some 4x4 matrix. Then you put I equals 1, my bad. I equals 2, H2 1, 4x4, I equals 3, 4x4. So how do you actually do this calculation? When you put I equals 1, you will look at these parameters, 0, 90, L1, theta 1. You will then go to here, you'll put the corresponding values here. So you can see alpha I, theta I, Si, Di, all those will go here. This will basically give you what the H is. So this is how you compute these individual homogeneous transformations. Now we are interested in computing the position of the end effector. So we need H3 with respect to 0. So that would just be H10, H21, H32, which, by the way, would be something like this: O30, sorry, R30, 3001. Okay, this matrix here will be a 3x3 orientation matrix. I'll give you the orientation of the end effector, and this part here is going to be a 3x1 matrix. It's going to give you the position of the end effector, and that's it, and you're done. Okay, now what we'll do is this is just some theory which tells you how to compute the end effector. Eventually, you're better off creating a visualization of the manipulator. So how do you create a visualization or animation? So this is how you would do it. And I will try to relate this with two-dimensional example first, and then we'll see how to do it in 3 dimensions. So this is going to be first sort of a recap. So we need to now do animation. Or visualization. So we've done this in 2D, right? So for example, the example we've looked so many times in 2D is this two-link manipulator, O, P, Q. What we did there was we computed the position of the X and Y position of this point O, XY position of P, XY position of Q. So that would have 2 coordinates, 1, 2. So this is the XY coordinate. Then we did the same thing to compute, well, we did use the homogeneous matrix to compute the position, the XY position of point 2, and then the XY position of Q. So this is XY, XY. Computed O1, O2, P1, P2, Q1, Q2 using homogeneous transformation in 2D. Okay, so then once we did that, in order to visualize, we use this command called line. And in the line command, you need to specify the x coordinate of the first of. So if you want to draw a line like so. Then what you do is you specify the x coordinate, and then you specify the y coordinate. So x, y, sorry, x, both are x, both are y, right? And this command basically will draw a line from, got erased, this will draw this line. Similarly, if you want to draw a line for the second piece, P to Q, you'll do the same thing. Line P1, Q1, white and blue, orange. So P1, Q1, P2, Q2, and that will give you the second line. Yeah, so that's not new. So this part is something we've done before. It's just a matter of figuring out the endpoints. We need xy, xy, xy. Now you can extend the same thing to 3 dimensions. All you need is the xyz position of point O, xyz position of point P, xyz position of point Q, and then there's a 3D extension of this, which is basically you just specify the third coordinate. So how do you do this? I'm going to put it down. We'll use the homogeneous matrix which we've created. So this problem was also done in using DH convention. So that gives us the DH table for this and also the homogeneous matrix for this manipulator. So you could do this in 3-dimensional as follows. So first of all, we've computed H10, H21, H3. We've computed that from the DH. Now what we need to do here is we need H10, we need H20, H20 is H10, H21, and we need H30, which is H10, H20, sorry, H21, H32. Now, if you look at H10 closely, it'll actually give you R matrix 0, and then it'll give you the position of O10, 1. This is basically the position of point P. This term will give you R10, H20, O20, 0, 1, and this will give you R30, 0, O30, 1. Okay, so buried in this is the x coordinate, y coordinate, and z coordinate of O. Okay, so the x, y, z would be just that particular column. It'll have the 3 elements. Similarly, buried in here is going to be P1, P2, and P3. It's the x, y, z coordinate of point P. And then finally, buried in here is the x coordinate, y coordinate, z coordinate of point Q. Okay, so all this comes from the homogeneous matrix, which which basically comes from the DH table. And so then the final thing you need to do in order to create this animation is use the line command in 3D. In the line command in 3D, what you do is you specify O1, P1, that's your first argument, O2, P2, that's the second argument, and O3, P3, is a third argument. So the first one is the x coordinates of the 2 points, then the y coordinates, and then the z coordinates. This will essentially draw the line from O to P. Okay. Similarly, what we can do is to draw the line from P to Q. You do line P1, Q1, P2, Q2, P3, Q3. Okay, now this is I'm just in a way writing this loosely in the sense that the indices for Python are actually they don't start from 1, they start from 0. So this in Python would actually be 0, 1, 2. But I just want to put 1, 2, 3 because it's much easier to list this with 1, 2, 3 in this particular notation here rather than putting 0, 1, and 2. But in Python, you'll have 0, 1, and 2 because the numbering starts from index 0. Okay, so I'll provide you with two files. One is a 2-link and a 3-link manipulator. Things we've discussed in this 2 examples. The first one is the 2-link example. Let me just run this first. It's just an animation, nothing. Just gives, if you specify the 2 angles, it plots the XY position. Let me run this for a longer time. And you can go here. So sines, cosine, this basically function sets the DH. If you pass to it each line of the DH table, in the sense A, alpha, D, and theta, then it basically returns the homogeneous matrix H. Okay, and so what I do is I compute H01 by calling this function with the first line of that 2-link manipulator. I call again H12 by passing the second line. To get the end of link 1, I do, which is basically H01. Same thing I wrote down in my notes at the position of point O. If I want position of point P, the midpoint or the elbow joint, it's going to be H01 times H12, and then for H02, I need the XYZ coordinates. And then I need the end effector coordinates, which I get from H03. I see. Well, this is actually the elbow, and this is actually the end. This is actually the end effector. The shoulder joint for a 2-link manipulator is basically 0, 0, 0. So this is the elbow joint of a 2-link manipulator. This is the end effector. So I have it over there, and which is actually end of link 2. And then it's just a matter of I use plot to draw a line, but there is another command called line which you could use. And so running this gives you H01, H00, which is 0, H01, H02. Joining lines, it gives you this. Now I also did the 3-link example. I coded it up. This one uses a different toolbox, which you might have to install. Or maybe it's installed. I don't know. I don't think I did anything special to install it. It's the MPL toolkits. It enables you to plot in 3 dimensions. This is the 3R manipulator, I think. Let's see, which manipulator is this? Yeah, I have theta 1, theta 2, theta 3. This is the example 2 I did, not did this class, the previous class. In that example, there was a theta 1, there was a D2 and D3, I think. And then theta 2 and theta 3 was 0. Okay, so same idea. Get H0, H01, H02, H03. Then do line, line, line. So here I do line, line, line 2, and then I just plot it. So if you run this, run it. Well, that's the manipulator in 3D. It doesn't have the pretty visualization of a manipulator, but it does its job of showing me where exactly the end effector is, which is the end of that last link, the light blue link. So that's the end effector. And if I wanted, I could put a dot.